Hi and welcome back in a new OnScale video. So in this video I'll show you how to simulate this kind of 3D transducer. So you have piezoelectric material here, which is in between some backing and some epoxy, and it is all inside a steel case. And all of that is into water. And here you see the acoustic pressure result, which is fired by this piezoelectric material when voltage is applied. So this is multi-physics analysis coupled with voltage and acoustics. So let me show you what you will get at the end. So as you can see here, we are able to calculate the time it takes for the acoustic pressure wave to be fired from the transducer here and to go to the other side. And so we can calculate the time it takes to go from A to B in this time domain analysis. So let's start by cleaning everything up. And here I'm in the post process, so let's go back to designer mode. I close my current project and I'm opening a new project. So let's choose mechanical dynamic 3D model. And for this analysis, I will maybe more convenient to use millimeters. So let's use millimeter and let's call it 3D transducer example. Okay. So let's start by importing some CAD model that I have of this. So here it is. If you look at the geometry, you have the 6 parts of this model, including the wire. So now it's only CAD, so I need to assign some material to it. So before I do that, I'll set up my frequency of interest in the project settings. So this will help for the automatic calculation of the mesh size. Let's put the same for the frequency of damping. Okay, now that this is done, let's go with the materials. So you can choose all the materials needed in this database. So I already have exported the material I need into an external file. So I'll just open this one. And as you see, I need those 1, 2, 3, 4, 5, 6 materials. So backing, hard epoxy, this is piezoelectric material, this is steel, this is urethane, and this is water. So you can find all those material in the database. So you just have to open each of them, select, and just add them to this if you're trying to follow up this tutorial. Now the only thing you must be careful about is for the piezoelectric material, which is this PMT3. You have to go in piezoelectric property and change the polling. So by default, it will be set up to Z direction, but my model, as you see, the polling is in Y direction. So double click on this and change it to Y direction. So very important, otherwise you will not get the result. And this is a classic mistake people do. So, okay, so now this is done. Let's assign this material to my parts here. So for that, I can directly like that click on the parts. So this is the water, and you see the color change in the walkthrough telling me that this is assigned. So my piezoelectric material is here. So maybe I'll hide the water to show you better how it looks. So it looks like that. This is the half transducer. I'll only simulate the half. I actually could simulate only 1/4. That would be even better, but you know, let's simulate half of this. So let's, I'm choosing this, a piezoelectric, so PMT3. This is the hard epoxy. This is the backing. Here I have some kind of encapsulation around it in urethane. And this is a steel casing. So let's assign steel. Okay. Okay, so my materials are assigned. Now that I did that, I need to define the loads and the boundary condition to assign to this. So the electrodes that will be defined around this PZT. And to define the electrodes, I need to define a forcing function first. So let's go in forcing function and assign recurve wavelet. So it's in time domain, it looks like that. In frequency domain, if you were to look in frequency domain, it looks like this. So the advantage is that it has a wide band of frequency. So you can simulate a lot of frequencies at the same time because this is time domain, right? This is time domain. So we'll look into the frequency domain by using fast Fourier transformation at the end. So don't forget to change the drive frequency, which is here 0.5 megahertz. So 500,000 hertz. Insert that. So, and before I assign the load, let's have a quick look at what the mesh will look like. So if you go into model graphics and you activate show approximative meshing, this will be the mesh size that will be automatically calculated for the grid, because OnScale use automatic grid to calculate and mesh your model. And you can change the size into configuration. So you have several methods, and because this is acoustic, this is wavelengths base, and the size recommended usually is like 15 elements per wavelength. So if I look here at this kind of size, it looks a bit small. Well, that will give me definitely good results, but for a first try, maybe I'll try something like 5. And I think this will give me around 5 elements around the PZT. Should be okay. Anyway, if it works, I can always increase that later. Now, the second thing to know is that because this is a grid, the elements or the nodes of the grid may not fall exactly on the right interface of your parts here on the CAD model. So that's why there is something called the key points. So key points will basically allow you to define some planes in all directions and the grid will be automatically matched to those planes. So you have to define those key points before you define the loadings, because the loads will take account of the key points. If you create the load first, then you might sometimes have problems. So first create key points, then the loads. So let's try it. Let's go into and add a new key point. So now I'm looking at the key point in the X direction. So for this demo, I will only add key points in the Y direction. But you have to know that actually, yeah, let's have a look at maybe let's do a rotation in the other direction. Have a better look like that. Yeah, I'll add some key points in Y direction. So you can first click on the screen like that. It will tell you the approximate location of this in this small window. So here it's 19.0 something. So I think the real distance is 19. So let's just input 19, place the points, and the plane will automatically be placed here. And let's click on this one. That's 23. So let's input 23, place. Okay, so I have 2 key points which will define that my thickness of my piezo is exactly at the right dimension. So in real application case, it's good to put key points everywhere on all the important dimensions of the model. For this example, I only put those 2 here to show you how it works. Okay, so now that this is done, let's hide the meshing. Let's hide those key points as well. Let's assign the loads. So let's hide the backing and also the hard epoxy. So I see only the piezo material. Let's click on loads. There's a plus here. Select the top surface. choose voltage and the time function. And here the area scaling, it's also important to set the right value. So if you go on OnScale website, you'll find a page like that on the support center called how to apply symmetry. And if you go down and you read that in detail, it will tell you that the value of the area scaling factor should be like the following. So if you have a 3D full model, nothing is required. If you have a 3D half symmetry, it should be 2. If you have 3D quarter symmetry, it should be 4. If you have a 2D model, then this should be multiplied by the Z length, and etc. Half 2D symmetry or 2D axis symmetric should be set up like that. So this value, this value of the area scaling is used to define the right size of the electrode. So for 3D model, it's automatically the surface is calculated, but if you have a 2D model, well, it doesn't know what is the real size of your electrode, so you need to input a Z value for your electrode. And in case you have symmetry like that, you just need to define it as 2 or 4, depending on if this is half or fourth symmetry. Okay, once this is done, just click on create the load. You'll see the load appears here. Now let's click on the other side, and this time this will be a ground. Create the load. Okay, so now I have my loads. Now let's set up the other boundary conditions. So you have domain boundaries where you can set up boundaries for all the minimum, maximum, and of X, Y, and Z axis. So in this case, don't forget that there is a water here. So if we look at this domain, the only boundary here where you have symmetry is this. So it is Z max. So let's go into Z max and choose symmetry. For all the other ones, for the moment it's set as 3. So if I set it as 3, the wave will actually reflect against those. So this is not what I want, because if the wave goes here and reflects, this will influence the results. So I want to consider that as an infinite water domain. So I want the borders to absorb the wave. So for that, I'll choose absorbing. For all the boundaries. So in case the absorbing boundary will not work for you, because sometimes this is a very, how to say, it's a very complex type of boundary condition. So sometimes it can lead to some divergence in the results. So then if you have this kind of case, just use impedance. So if you choose impedance boundary, generally this solves the problem, and your model is able to converge correctly. So for this model, it's okay, just choose absorbing. So, okay, and now for the analysis. So now we are setting up the analysis time for this simulation. So analysis time here should be, let's say, let's try like that. So this is 10 microseconds, right? 10 microseconds, yes. So you should calculate this actually if you want to be sure what simulation time you should run. And the way to calculate it is just to think about how long would it take to this acoustic wave to go from one side to another. In theory, if you take the velocity speed of the wave, which is defined in the material properties, so you look at, for example, the propagation of this wave in water, and there is the bulk velocity here, which is written, which is 1,400 meters per second, right? So you just take the dimension of this volume and you take this velocity, and this allows you to calculate which is the time, theoretical time to go to this wave to travel. And then that will allow you to define the analysis simulation time So after that, you can change it in function of what do you really need. Now that the analysis is set up, let's set up the output. So the output is basically what kind of results I want to get out of this model. So click on the plus. So you have various types of results. You can get time history curves, time average, field data, extrapolation data, shape data, or data snapshot. The basic one I'll set is a time history curve, and I'll define a certain position. So you see you have a small, well, it's very small, but okay, let me zoom. You have a point here which tells you where my acoustic pressure time history probe will be put. So in this case, for the Y direction, I want it here at the output. So I know the acoustic wave which is fired from here. And let's put another one here. So let's just put another. And I think should be 130 if I'm not wrong. Okay, yeah. So you see I have the second probe here. So I'll be able to see the signal going from here and the signal arriving from here, which will allow me to calculate the travel time as well. Now let's also output data snapshot. So data snapshot means that I'll output the acoustic pressure at a certain time of the analysis that I decide. So by default, this is defined in the runtime graphics as a number, well, first define certain number of views. This is the number of frame that will be output will be equal to the number of snapshot outputted. So if I want, I don't know, 200 snapshots in my analysis, I can define it here. So if you're using the cloud, I recommend you to define low number of snapshots because this will influence the calculation also, and also the data size that you will have to download. So better to use 10 snapshots or something, or not use snapshot. Anyway, now let me show you with the basic option. So I have those three defined, and so the runtime graphics here I'm defining is basically what I will see when I run the analysis. I will have a dynamic visualization. So I want to see this, let's say the output 1, and I want to see my acoustic pressure. So let's now calculate all that. Now the model is ready. So I'll use first run local to have a first overview and calculate on my machine. I could also use the cloud to calculate that. So as you see, as my mesh size seems okay. It seems okay. So it's running and launching simulation. So here okay, so the analysis seems to be a bit short. So it's only calculating a part of the input. So I may have to increase the simulation time. Let's increase that to 5 times. And let's run that again. So my computer starts to protest. So you can hear my processor is very loud, unfortunately. So that's also advantage of using the cloud because it doesn't use your computer, your local resources, so you can launch as many simulations as you want and still work on your model without any problem. But anyway, this is so okay. So this is calculated. So you see a transducer here. This is the wire, and this is my acoustic wave. So this is the acoustic pressure results, and you see that the waves is arriving. So I calculated now 20 stages. Okay, I'm still a bit short for the analysis time. I guess I will need double of that to see the wave arriving. So let's increase that, and this time let's use the cloud to calculate. So I'll show you how the cloud works. So for the cloud, let's use, I can increase the number of CPUs used. This is the good thing. Let's estimate and see how long this will take. Okay, 2 minutes. Let's run that. Oh, with 2 CPUs. Okay, with 16 CPUs, it's a bit faster. Let's just run that. When your calculation is finished, go to storage and just download your data. Sometimes you may have to wait 1 minute to get all the results here. Make sure they are here before you download. So once the results are downloaded, go to the post processor and just open those results. So go to the folder where those results have been downloaded. You see you have in the File Explorer, you have 3 types of results: snapshots, and you have one which is called FLX data, which contains basically, well, here I didn't set up this kind of data, so it won't appear, but it contains field data. So you'll see, like in the snapshot. So in the snapshot, you contain also field data, but it's listed by time frame. So I have 20 instants, like explained previously. So we'll have 20 results for the acoustic pressure. So going from this time, second time, like that. And it's basically a snapshot all in 3D of the wave going from the start to the end. And if you right click, you click on plot data over time, you're able to get an animation like that. So you can click on play to play the animation, or you can save the video into an MP4 file. Now, the results that interest me are the one also included in the FLX HST file, which are the time domain curves. So let's configure the viewport like this. On this side, I'll put basically this 3D model. On this side here, I'll have a look at my acoustic pressure. So yeah, so this is the acoustic pressure at the output, the second position. This is at the first position. So you see, you can actually put them on the same as well. You see that this is matched on the same graph. This is the input. This is just at when I put the probe at the input. So this is how it looks, and this is how it looks when it arrives here at the output of my water. And you see the decrease in amplitude of this wave. And well, there are many more things you can analyze. You have, by default, you have the charge and the voltage at the electrode as well that I can display. Let's reset this viewport here, and this is the charge at my electrode here. And let's reset that, and this is the voltage. Yeah, voltage is basically equal to my force input function. Okay, and that's it for today's tutorial. I hope you it was useful for you, and you're now able to simulate this kind of 3D transducer with OnScale. If you have any comments, something you don't understand, something you want to know, leave some questions inside the videos or wherever this video is embedded on the web page. Let me know. So thank you very much for watching. If you like this video, please leave a like. Thank you. Thank you so much.